Many communities use a water tower to supply water under pressure to homes as in the figure below. The top of the water tower is open to the air so that the pressure above the surface is 1 atmosphere. When you open the faucet in your home, water comes out. The radius of the opening of the water faucet is 5 millimeters. A, what is the velocity of the water as it leaves the faucet? B, what is the volume rate of flow, cubic meter per second? And C, calculate the time required to fill a 1 liter bottle with water. This is a fluid problem, and so we'll be using the Bernoulli principle to solve the problem. The Bernoulli principle is applied by locating two locations within a single fluid and connecting them via Bernoulli's principle. We'll choose our two locations as, number 1, the top surface of the water in the water tower, and number 2, the water as it exits the faucet in your home. In connecting location 1 to location 2, we'll call upon the Bernoulli principle, which says that the quantity pressure plus 1/2 density times velocity squared plus density times g times height, which we'll call y, takes the same value at all locations within any single fluid. The way we build a useful equation is we total this quantity at location 1 and set this equal to the same total at location 2. In any Bernoulli problem, we have our choice as to whether we will use absolute pressure or whether we will use gauge pressure. Gauge pressure is 0 in the atmosphere that we all experience, and absolute pressure is, of course, 100,000 pascals. In this problem, since the water is in contact with the air at both location 1 and location 2, it will be simplest for us to use the gauge pressure, which will be 0 at both locations. Location 1 is the very large surface area at the top of the water tower, and so we can neglect the velocity at this point as compared to the other terms. Whether we have a potential energy term, of course, depends upon where we would like to call y equals 0, and I think I will call that at the location where both of our heights are measured from, and that's the ground, meaning that at location 1 we have a height of 10 meters, so that our Bernoulli term is 1,000 kilograms per cubic meter times g times a height of 10 meters. At location 2, since the water is again in contact with the air, it has the same pressure as the air, which is a gauge pressure of 0. At this point, the water is certainly moving, so we will have 1/2 the density of water times the velocity at location 2 squared. And since we defined y equals 0 to be at the ground, we will have a potential energy term at this location, which will be the density of water times g times a height of 1.5 meters. Clearly, we could have chosen the faucet itself as our definition of y equals 0, yielding no gravitational potential energy term on the right-hand side, and a term of 1,000 g times 8.5 meters at location 1. Had we done it by this alternative technique, we would still get identically the same answer. The velocity v2 is equal to the square root of twice g times 8.5, which is 12.9 meter per second. In part B of the problem, we are asked to quantify the rate at which the water flows out of the faucet. There are two common ways to quantify the rate at which a fluid moves. The first is density times area times velocity. This quantity has the units of kilogram per second and applies both to gases and to liquids. However, in the case of liquids, we typically assume that the density will be the same at all locations, so that we often calculate instead the simpler quantity, area times velocity, which is the cubic meter per second of the liquid. The area of a circular opening will be pi times the radius squared, which we then multiply by the velocity with which the water leaves the pipe to yield the volume rate of flow of 0.00101 cubic meters per second. Finally, we're we're asked to calculate the time required to fill a 1-liter bottle with water. Examining the units of the appropriate quantities, liter will be a volume, and if we divide this by the volume per second, we'll come up with a time. However, since the volume rate of flow that we calculated in the previous part of the problem is listed in cubic meter per second, we need to convert our 1 liter into cubic meters in order to proceed. We recognize that 1 liter is equal to 1,000 cubic centimeters, and so we will multiply by cubic centimeters and divide by liters. Next, we recognize that we need to eliminate the centimeter unit in favor of meters. Doing so, we would put meters in the numerator and centimeters in the denominator, and we recognize that 1 meter is the same distance as 100 centimeters. However, since the quantity at hand is centimeters cubed, we'll need to repeat this operation 3 times in order to succeed. This tells us that 1 liter is the same quantity as 0.001 cubic meters. To answer the question at hand, we take our 0.001 cubic meters and we divide this by the result from part B. Here we've accomplished the division by placing the 1 second in the numerator and the 0.00101 cubic meters in the denominator, so that we find the time interval required to fill this bottle of water to be 0.987 seconds, and the time interval is so short because we've got the faucet turned on full blast.